simulation, the logic is correct, but whether the hardware is created, no, hardware is not created. So you run the RTL analysis. So under RTL analysis, what is there? You can know the RTL schematic of this. Open RTL analysis, elaborated design if you open, so it will give the data flow of this. So okay, if you give, so it will give the just the data flow from the input data is coming, where the output data will go. So this will be the elaborated design. See, the sum and carry, I think it is okay. Circuit is okay. So circuit it has made. Now what you have to do is run the synthesis. So up to this, the simulation is okay, the circuit they have made is okay, but the hardware is not yet created on chip. So you have to synthesize. Run synthesis you have to give. So run on the local host. So number of jobs means 4 parallel process will be going on. So you just create OK. And now synthesis, when it is running, it is showing this one in the queue. So here it is moving. So you will see synthesis is going on. When it is stopped, it will give the result. Now run implementation you don't do. You open the synthesized design. First you see what after synthesis, how in the chip it is synthesized. So do you want to close the elaborated? It will close this window. Yes, you do, yes. So initializing the timing, what they have got from this simulation. And then see, this is the chip actually it has created. Here
it is a chip.
It is a floor plan. I told you that in ASIC you have to make this by hand in ASIC flow. But here it is FPGA flow. The algorithm is automatically, the Xilinx software is automatically doing this and creating this floor plan. Under this floor plan, where your code is there, you have to double click it. Here it is not there. Double click is, you cannot find any wires here, because the design is very small, and this FPGA is see here one dot is there. So here you can see when you place the mouse, see column 61 sites M9 L10 XADC X0Y0, clock region is X0Y3. So X0Y3, this coordinate is there. Under this the site is this one. So here you see, here also it is there, here it is not there. So in these two blocks some logic has been placed, and here it is, here also some logic is placed, like that it is there. So this is the synthesized design. Now this is the floor plan view of the design. Now when you put it in back, you can do the, now you do the schematic of the, no, this is separate, elaborate design you don't do. Now the schematic, without synthesis you have seen the circuit. Now after synthesis you see the circuit. Schematic here. See, now the circuit has been replaced by LUT. LUT means the lookup table. Now no XOR gate and some those things are not there. Now that has been replaced by the components of the FPGA.
Okay.
So this, and this is the O buff means output buffer, and this is the I buff means input buffer.
Okay.
And this symbol stands for the tri-state. Okay, carry and the sum. This symbol stands for the input and output. Those are tri-state. Huh. Now what 6 cells are there, 4 input output ports are there. I told that cell library, so 6 cells are there here and 4 input output ports are there and 8 nets are there. Net means these wires actually. Okay, so under LUT there is no sub block, so this is the lowest block. Okay, now what you do is you report power. Let's see, here is power underscore 1 profile. Under power underscore 1 you can get the thing, so it will have to be okay. Oh, sorry. Now you go to this okay. Okay. Now here see the power thing has come. Power graph has come. See on chip power it is showing. See 84% and 16%. So what is 84%? 84% is dynamic power and that is 0.682 watt and this one 16% is the device static power. Okay, so 95% is the IO power. I mean input output itself is taking 95% power. So the main logic power is less, so 0.004 watt. And the signal power is 0.026 watt, this much, only blue color. So only input output number of pins will take more power. So that you have to reduce. How to reduce, I will tell you. So this is the junction temperature is at 27.7 degrees centigrade and total on chip power is 0.817 watt. So this is one power report. Timing report, you have to see the report project summary. Project summary, you see that here some utilization synthesis report is complete. Now DRC violation run implement. For DRC violation, that means the design rule checking violation, you have to run the implementation. So let's run, and for timing information you have to run the implementation. And power you have already got. Now that is the pre-synthesis power. This power again after implementation there will be power. So this power and that power should match. Means before implementation the estimation of power is this, and after post implementation, that means post placement, routing and those things are done. So though that power, whether it will change or not before synthesis, after synthesis, let's see. So we have done already synthesis. Now from the left hand panel, you run the next thing is run implementation. So divide, launch, run on local host and okay. So you okay this one, it will run, it is running. Now it is initializing the design, and after that it will show that placement will be done, then floor planning will be done automatically. All algorithms are running on the back end of this software. So now they are doing the physical design on back end. Okay, so optimizing the design, then placing the design, running placement, then routing the design. It will take some time. After that it will show. Actually it is mapping the cell library to the real circuit. implementation is complete. Tick. Now open the implemented design. Don't generate bitstream because you have to fix the board for that. I will show with the board also. So open the implemented design. Okay. Now do you want to close the synthesis? Now it will close the previously synthesized design. So you tell yes, close the synthesis, and then it will open the initializing timing. So now timing information will come.
Okay, sir.
So in the report you can see the timing reports now. See here the worst negative slack is infinity. So there are no user specific timing constraints. I did not give any constraint at the beginning, I told you. So it will, without the constant, this is the total negative slack, this is the hold slack, and these are not applicable because I did not give any timing constant. Now I will tell you how to give the timing constant. Now total number of endpoints is 2, total number of endpoints is 2. So this is the timing report they are showing, and here project summary. Now you see, now some timing you can see here timing, now something came. Previously no thing was there, run implementation was there in the timing report. So now some words negative slack. Always remember that the slack should be positive. If slack is negative, then the constants are not met. So see, 2 critical warnings are there, 1 warning is there, but no error.
No.
Whenever there is no error, it is okay, but critical warning sometimes may stop from mapping into the real mode. So you have to see some critical warnings. So implemented DRC report also you can see from here. So these are the 4 out of 4 logical ports, IO standard and default. These things you can read from here. They are telling how they have mapped and all the logical thing, everything, ground and voltage, about all the things they are telling. Which port is mapped and what are the informations regarding this.
Yes.
Now in implementation, now you have opened the implementation design. So now you can see the schematic of the open design. So here you again, this is the schematic after implementation, LUT2, and you see whether it is something changed or not, or it is the same thing. Achha. It is almost the same thing because it is the optimized design. And now the power timing, now again you see the report power after in implementation column. Run implementation, there is some report power. Now again report power, again this will be power. Suppose you give power 2 profile, because power 1 we have already created, first one. Now in this one you